Hello, everybody. Okay, let's go ahead and get started. So, we're kind of going to review some geometry today. So, we're going to start with the Pythagorean theorem. So, we should hopefully know that the Pythagorean theorem it works for right triangles, and it says that a squared plus b squared equals c squared, where a and b are both legs of the triangle. So, they're the shorter side. So, would be a leg, and this would also be a leg, and then across from that right angle is the hypotenuse. So it doesn't matter which leg is A and which leg is B, as long as you're doing leg squared plus leg squared equals the hypotenuse squared. Okay. So again, the two shorter sides, each of them squared, added together, should equal to the longer side squared. And with that Pythagorean theorem, there is also a converse. So again, we always want to make sure that C is the longest side, and it is across from that right angle. But with the converse, it doesn't necessarily have to be a right angle. So the converse says that if we get a squared plus b squared equals c squared, if they are equal, what that means is we have a right triangle. But there are two other cases. So if we do a squared plus b squared is less than c squared. So if we plug these in, again, c is the longest side, and we get that a squared plus b squared is smaller, then that means we actually have an obtuse triangle. And then finally, if we do a squared plus b squared is greater than c squared, that means we're going to have an acute triangle. So these are kind of the three options, which again makes it a converse because instead of proving the Pythagorean theorem, because we're given a right triangle, we're going the other direction and saying, what kind of triangle do we have, kind of using that Pythagorean theorem. All right, and then we should also know that special right triangles exist. So there's two types of special right triangles. The first one is a 45, 45, 90 triangle. And so this happens when we have two congruent sides. Each of those would be called n per se, and we have 45 degrees in each of these angles. So when that happens, each of those legs, each of those congruent sides would be the length n, and then the hypotenuse would be n times the square root of 2. You can do the Pythagorean theorem to get this, but we want to use special right triangles as kind of like a shortcut. So the other one is a 30, 60, 90 triangle, and this is a little bit different. So the shortest side should be across from that 30-degree angle, and we go based off of that. We call that n, or our shortest side. So then the longer leg, which should be across from that 60-degree angle, we'll take that shortest side and multiply by the square root of 3. And then our hypotenuse, which is across from the right angle, we'll take that n and we'll double it. So again, we're always wanting to get back to that shortest side if we can. Okay, so we're going to go through some of these. So this says find the missing lengths, even if they're not labeled, and leave your answers in simplest radical form. So this first one, we should note that we have a 45, 45, 90 triangle, which means both of these are congruent. So if we're looking at this and we're referencing back to this kind of figure, we know that those two legs would be n, and the hypotenuse would be n root 2. So we need to be able to solve for that n in order to get those missing lengths. So what we would do is we'll set 9 equal to n square root 2, and we'll solve. So we will divide both sides by the square root of 2, and we'll get that n, that thing we're trying to base everything off of, is 9 over the square root of 2. Okay, which means both v and u are going to equal 9 over the square root of 2. Now, there's one thing that I am going to show you, which is called rationalizing. I'm not going to require that you rationalize, but it is kind of a good thing to see. So rationalizing is when we have that 9 over the square root 2, and somebody many moons ago was like, hey, I don't like that you have radicals in the denominator. It's gross and I don't like it. So what we do instead is we multiply both the numerator and the denominator by that radical in order to kind of get rid of it. So when we do that, we'll get that the numerator is 9 square root 2. And square root 2 times square root 2 is going to be like the square root of 4, which would just simplify to 2. So both of these are equivalent, these two pieces. So you can write it either way. I'm not going to be particularly hard on the rationalization. I just want you guys to see it, to know that it does exist. All right, and so that's how we get our answer there. Well, whatever. Okay. So the next one we should note is a 30, 60, 90 triangle. We see this because of the 30 degrees there, which means this angle is 60 degrees. So again, our n, or our shortest side, is going to be across from that 30 degrees. Our n root 3 is going to be kind of that longer side, our longer leg, and then our hypotenuse is going to be 2 times n. So again, we're going to use the information that we have, which are these two, in order to solve for n and go from there. So we'll say, okay, 4 is equal to 2n. So we'll divide both sides by 2, and we'll get that n equals 2. So that means that b, right over here, b is going to be 2. And then to get a, all we're going to do is take that n, that 2, and we'll multiply it by the square root of 3. And so these two would be our answers. We don't need to rationalize anything because we aren't dividing by any radicals. So these would be our two answers there. Alrighty. This one is a little bit more complicated because we kind of have two figures going on here. So I would probably work with one that we're given information on first. So I'm going to work with this one first, right? Because we have some information on it. We're actually given a side length, and we eventually want to get to x. But again, it asks us to solve all the sides, regardless of whether it's labeled. So I'm going to call this a, and I'm going to call this b, and I'm going to call this y, just so that we can solve for all of those sides. So starting with a and b, again, we have a 30, 60, 90 triangle here. So that means across from that 30-degree angle, that's our shortest side. That's like our n, right? The across from the 60-degree angle, that's going to be like our n root 3. And then across from the 90-degree angle is going to be our 2n. Again, that's going based upon this 30, 60, 90 rule. So that means that for that first piece, we have that n is equal to 9 square root 2. So that's already solved for. We don't need to solve for it. So to get a, what we need to do is we need to take that 9 square root 2 and we'll multiply it by 2, right? Because we're doing 2n. So when we're multiplying these, we can only do outside numbers with outside numbers and inside numbers with inside numbers. So we'll just do 2 times 9, which is 18, and then that square root 2 would kind of just stay there. Similarly, to find b, we're going to take that n, which is 9 square root 2, and all we're doing is we are multiplying by the square root of 3 here. And again, both of these are under the radical, which is fine. So that 9 will stay the same, and we'll do 2 times 3 to get the square root of 6. And that doesn't simplify, so we'll just kind of leave it alone there. So that was our first figure. And so I'm going to kind of erase these n's now that I know those values for a and b. So I know that b, which I'm going to have to use kind of in my next picture, is 9 square root 6. So now I'm going to jump over to the next figure, this one, and try to find x and y there. Okay. Which hopefully we should see that that is a 45, 45, 90 triangle. So we have this one, and this one should be the same length. Again, both of those are legs. Both of those should be considered our n. And then our hypotenuse, which is this other side that it kind of shares with the figure, would be our n times the square root of 2. Again, that's why I do kind of like to color code these, because you can, n is going to change between these two different figures. So again, we're using this rule. So we'll say that 9 square root 6 is going to equal n square root 2. And then we need to solve for n. Okay, so we'll divide by the square root of 2. Again, this is like the second n that we have here. And so we can actually divide these radicals. So the 9 is going to stay the same, but we can do the square root of 6 divided by the square root of 2, which 6 divided by 2 is going to give us the square root of 3. So what that gives us is in this other figure, both x and y are going to be 9 times the square root of 3. Alrighty. So we are looking at this image. Again, we want to start with a triangle where we're actually given a side measure, which here is where we would be given that. So this is a 45, 45, 90 triangle. We see that because of the degree measures, which means this is going to be congruent to this, right? I'm going to call this A and this B because, again, it asked me to find those. So what this means is for this image, again, this would be our n, this would be our n, and this would be our n square root 2. So that means that A is going to be equal to n, which is 6, right? N in this first figure is 6. We see that here. And so in order to get B, all we need to do is take that 6 and multiply it by the square root of 2. So it'd be 6 square root 2. And that allows us to solve kind of that first figure. So once we get that, we can hop on over to that second figure, which this one we should hopefully see is a 30, 60, 90 triangle. So here, that shortest side again is across from the 30 degrees. So this is going to be our n now. So then the longer leg is going to be n times the square root of 3. And the hypotenuse, which I'm going to call y, is going to be 2 times n. So we have to kind of find this like new n now. So in this second figure, that n is the same thing as the b, the hypotenuse from the previous problem. So in that second picture, n is going to be 6 square root 2. Again, the same thing as the b that we just found. So to find x, we need to take that 6 square root 6 square root 2 and multiply it by the square root of 3. So that's going to give us, again, we'll multiply what's inside by what's inside. So 2 times 3 is going to give us 6. So we'll get 6 square root 6 for that. And then to find y, we'll go back and we're multiplying 2 times that n, which is 6 square root 2. And we'll multiply what's outside by what's outside. 2 times 6 is going to give us 12 square root 2. And we'll have solved that whole triangle because we solve for every single piece. Again, I do have kind of 2 different ends there, so just be really, really careful that you're not mixing those up. All right. So on to the next one. So we're going to talk about some trigonometric functions. Some of these you may have heard of before. We want to let theta be an acute angle of a right triangle. So it can be kind of either angle, but for this purpose, we're going to use this one. And we have 6 trigonometric functions of the angles that are defined below. So the first one is what we call sine. So it's really S-I-N-E, but S-I-N is kind of the abbreviation. And it is the opposite over the hypotenuse. And then we have cosine, which is the adjacent over the hypotenuse. And we have tangent, which is the opposite over the adjacent. You may have heard of these before in the term SOHCAHTOA. Right? Sine is the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. Tangent is the opposite over the adjacent. But what we're also going to introduce is other types of trig. So there are 3 more different trig identities that we have. And so this first one is called cosecant. And it's basically if you took sine and you flipped it. So it is the hypotenuse over the opposite. And then we have secant, which is if you flipped cosine. So it is the hypotenuse over the adjacent. And then we have cotangent, which is the flipped tangent, the opposite, the adjacent over the opposite. So if you can remember that SOHCAHTOA and you can remember which ones are flipped of the others, you should be good to go. The tangent and the cotangent's kind of easy to remember. I remember cosine and secant as one starts with C and ends with S, and the other one starts with S and ends with C. So those kind of help me to remember that those two are opposites of one another. And then sine and cosecant are just kind of remembering the terms. So we're going to actually do this with an image. So this says find the exact values of the 6 trigonometric functions of the angle theta in the triangle. So this is the angle we're working with here. So the first thing we need to do is actually figure out what is the hypotenuse. So we see that this is a right triangle. That means we can do the Pythagorean theorem. So this would be like our 3 would be like our a squared, 4 we would do b squared, and we'll set that equal to c squared. So 3 squared is 9, 4 squared is 16, c squared. So we'd have 25 equals c squared. And we take the square root to get that c equals 5. So that hypotenuse there is going to be equal to 5. So again, we're working with that SOHCAHTOA. So if this is the angle we're working with, sine is going to be the opposite over the hypotenuse. So sine is going to be the opposite, which is 4, over the hypotenuse, which is 5. Cosine is going to be the adjacent, which is 3, over the hypotenuse, which is 5. Tangent is going to be the opposite, which is 4, over the adjacent, which is 3. So now we can think about kind of the rest based off of what we already found. So cosecant is really just sine flipped. So it is the hypotenuse over the opposite. So it's going to be 5/4. Secant is the opposite of cosine, or the flipped version of cosine. So it's going to be the hypotenuse, which is 5, over the adjacent, which is 3. And then tangent and cotangent are the reciprocals of one another. So this would be the adjacent, which is 3, over the opposite, which is 4. And so those would be all of our trig identities. Alrighty. So this one says sketch a triangle corresponding to the trigonometric function of the acute angle theta, and then find the other 5 trigonometric functions. So again, first of all, we already know what sine theta is. It's 2/5. We see that from the problem. But we're going to use that in order to draw a picture. So we're going to draw a triangle. Okay, looks something like this. And I'm going to call this angle theta. So with sine, so again, SOHCAHTOA is what we're thinking of. Sine, we know, is the opposite over the hypotenuse. So this tells me that 2 is going to be opposite of that theta, and that the hypotenuse is going to be 5. So what we're allowed to do there is we need to kind of solve for that other side now. So I'm going to call that b. And again, we're going to do the Pythagorean theorem in order to solve that. So we're going to say 2 squared plus b squared equals 5 squared. So we'll get 2 squared is 4 plus b squared equals 25. We'll subtract 4 from both sides. So we'll get that b squared is equal to 21. And then we would take the square root. So b is going to equal the square root of 21. Typically, it would be kind of plus or minus, but here we're not going to have a negative side length. So we're okay to just leave that as the square root of 21. Okay. And then we can find our other trig identities now that we found that. So again, we can find cosine by saying, okay, cosine is the adjacent over the hypotenuse. So cosine is going to be the square root of 21, which again doesn't simplify. It splits into 3 and 7, but neither of those are perfect squares. So it'd be the square root of 21 over 5. And then tangent would be the opposite. The opposite over the adjacent. So 2 over the square root of 21. Now, if we did want to rationalize that, just to get us some practice, again, we would take 2 over the square root of 21. We'd multiply both by the square root of 21. And so that's going to give us 2 square root 21 over just a regular 21. Right? Because when we multiply a radical by itself, the radicals are going to cancel. And 2 over 21 doesn't reduce, so we would leave it like that. Alrighty. So then we would want to find cosecant, again, the reciprocal of sine, or the hypotenuse over the opposite. So we would say 5 over 2. Then we would find secant, which is the reciprocal of cosine. And so that's going to be 5 over the square root of 21. Again, if we did want to rationalize that, we would multiply by the square root of 21 over the square root of 21. So we would get 5 square root 21 over just a regular 21. Again, you don't have to do that. I'm just showing you that it does exist. And then we would do cotangent, which is the reciprocal of tangent. So this one is going to be the square root of 21 over 2. And then we found all of our trig. And we can move on to the next problem. Alrighty. So the next one we're given is cosecant. So cosecant is the opposite of sine. So sine we know is the opposite over the hypotenuse. So cosecant is going to be the hypotenuse over the opposite. But you may be looking at this and be going, but that's not a fraction. We kind of have to force a fraction here. So we would say, okay, this is technically speaking 9 over 1. And so we do have to force a fraction. And again, this is the opposite of sine. So it's going to be the hypotenuse over the opposite, and we'll use that to create our triangle. So again, we already know cosecant is 9. We can fill that out. We're good to go there. And then we'll kind of create our triangle. So again, we have a right triangle. I'm still going to call this angle theta. We know that the hypotenuse is 9 because that's the number that's on top, and we know that the opposite is 1. We do need to find this little piece down here. So again, we're going to have to do that Pythagorean theorem. So we'd say 1 squared plus b squared equals 9 squared. 1 squared is 1 plus b squared equals 81. We'll subtract 1 from both sides. So we'll get that b squared equals 80. And then we would need to simplify this, right? So we'd get that b is equal to the square root of 80, which is 16 times 5. So the square root of 16 is 4, and then it'd be root 5. Now, if you don't see that, you can do the birthday cake method, which we would say, okay, what is 80 divisible by? It's divisible by 2, so that's going to be 40. That's divisible by 2, which is going to be 20. That's divisible by 2, which is 10, 2, which is 5, and then 5, which is 1. So you would do couples come out. So we have a couple of 2's and a couple of 2's, and singles stay home. So that first couple, we would do 2 times 2. Again, that's giving us the 4, and then the square root of 5. So either way, you can get that same answer. Alrighty. So moving on to find the other kind of trig. So again, sine is going to be the opposite of, or the reciprocal of cosecant. So again, now we know that this is 4 root 5. So it's, instead of 9, it's going to be 1 over 9, right? We're taking that fraction and we're flipping it. Cosine is going to be the adjacent, which is 4 root 5, over the hypotenuse, which is 9. And tangent is going to be the opposite, which is 1, over the adjacent, which is 4 root 5. Again, that one I would actually you can attempt to rationalize. The way that we would do that is if I have 1 over 4 root 5, all I'm going to multiply by is just the radical to kind of get rid of it. So I get the square root of 5 in the numerator, and then the square root of 5 times the square root of 5 is just going to be 5. 5 times 4 is going to give me 20. Alrighty, and then secant, again, is going to be the opposite of cosine. So we would flip that fraction. So it's going to be 9 over 4 root 5. Again, we can rationalize that because we can take 9 over 4 root 5 and we can multiply by the square root of 5. So again, we'll get 9 square root of 5 in our numerator, and similar to that tangent problem, square root of 5 times square root of 5 is 5. 4 times 5 is going to give us 20. I'm okay with you not rationalizing. I just want to show you that it exists. And then lastly, we would do cotangent, which is again going to be the opposite of tangent, or the flip fraction. So it's going to be 4 root 5 over 1, which instead of putting it over 1, we can just leave it as 4 root 5, right? Because over 1 would be the same thing. And so this would be all of our trig. Alrighty. Okay, on to the next problem. So we're given tangent here. We know that tangent is the opposite over the adjacent. And so again, we're going to draw a picture. So we'll have this be our theta. We know that opposite of that theta is going to be the length of 1, and adjacent to is going to be the length of 4. And we want to try to find that hypotenuse first before we can do anything else. So we do 1 squared plus 4 squared equals c squared. So 1 squared is 1, 4 squared is 16, and that's going to equal c squared. So c squared equals 17, which means c is going to equal the square root of 17. That does not simplify. It doesn't split up at all. It is a prime number, so it's just going to kind of stay like that. Alrighty, so first we'll find, again, we already know what tangent is. We know it's 1 over 4 from the original problem. So we'll start by finding sine. So sine is going to be the opposite over the hypotenuse. So it's going to be 1 over the square root of 17, with the option to rationalize there. Right, we'd multiply by the square root of 17. And so we'd get the square root of 17 over just a regular 17 when we do that. Again, if you're not super confident on rationalizing, you don't have to do it. But again, I'm just showing you that it exists. So then cosine would be the adjacent over the hypotenuse. So it's going to be 4 over the square root of 17. Again, with the opportunity to rationalize. We'd multiply by the square root of 17. So it'd be 4 root 17 over a regular 17. And again, tangent we already know. So cosecant is going to be the flip fraction of sine. So again, we're just going to flip that fraction. So it'd be the square root of 17 over 1, which we can just write as the square root of 17. Secant is going to be the flip fraction of cosine. So that's going to be the square root of 17 over 4. And tangent is going to be the flip fraction of cotangent. So that we would flip that, it would be 4 over 1, which again we would just write as 4. Alrighty, I'd like you to try this one on your own. So we have secant here, which is the opposite of cosine, right? The flip fraction of cosine, the reciprocal. So this is actually going to be the hypotenuse over the adjacent. And again, we're going to draw our picture. Okay, so we have that this is theta. The adjacent to that is 2, and the hypotenuse is 9. So we need to find that missing leg. So we're going to do 2 squared plus a squared equals 9 squared. 2 squared is 4. We'll have a squared, and we'll have 81. So we'll subtract 4 from both sides to get that a squared equals 77. So that side length is going to be the square root of 77. Again, that splits into 11 and 7, but that doesn't really give us anything. So we'll just kind of leave it as the square root of 77. So next thing that we'll do is we'll find sine. So sine is going to be the opposite, which we just found to be the square root of the 77 over the hypotenuse. So we'd say square root of 77 over 9. The cosine is going to be the adjacent over the hypotenuse, so it's going to be 2 over 9. And the tangent is going to be the opposite over the adjacent. So it's going to be the square root of 77 over 2. The cosecant is going to be the reciprocal of sine. So it would be 9 over the square root of 77. Again, you did have the option to rationalize there. If you did rationalize, it would be 9 square root of 77. You should multiply by the square root of 77. And so that would be 9 square root 77 over 77. Secant, again, we were given in the problem, so that's going to be 9 over 2. And cotangent is going to be the reciprocal of tangent, so it should be 2 over the square root of 77. And we would get, again, you can rationalize that if you'd like to. So 2 over the square root of 77 multiplied by the square root of 77. And you'd get 2 square root 77 over 77. Again, you don't have to rationalize if you don't want to. But that should be the whole thing. And have a great day, guys.